This is slide number 48 and I am your presenter Asloob Mudassar. Fraunhofer diffraction by a thin sinusoidal amplitude grating. An amplitude grating of size 2W by 2W, that is, we are using a square grating centered at the center of the zeta eta coordinate system, that is at zeta is equal to 0, eta is equal to 0, coincident with the zeta eta plane, has an amplitude transmittance TA as a function of zeta eta is defined in equation number 96. So TA of zeta and eta is equal to 1 plus m into cos of 2 pi 1 over L zeta for all values of eta, and multiplied by the two rect functions, rect of zeta over 2w multiplied by rect of eta over 2w. So you see that this is on the left hand side we have a grating, mathematically defined the grating which is of infinite extent, and the two rect functions actually limit the dimensions of that one into size of 2w by 2w. Okay. Capital L is the separation between two consecutive grating lines called the pitch of the grating. The reciprocal of this quantity gives the spatial frequency of the grating. The grating lines run along the eta direction. So you see that this 1 over L appearing in equation number 96 is actually the spatial frequency of the grating, and L is actually the separation or the pitch of the grating, separation between the two consecutive lines or the pitch of the grating, and 1 over L is the spatial frequency of the grating. That is how many line pairs are there in per millimeter or per centimeter or per inch, whatever units you choose. And the grating lines are parallel to the eta axis. The plot of this grating function for three different values of m has been given earlier. Under the illumination by normally incident unit amplitude plane wave, discarding the constant phase factor, the field just after the grating is as given in equation number 97. So you see that now we have replaced TA in the as a function of zeta and eta in the equation number 96 by the field value which is u of zeta comma eta. So this is the field, and you know that this field is written when TA in the above equation is multiplied by 1, because 1 is the amplitude of the plane wave which is incident, and you know that since the plane wave is normally incident, the constant phase factor that will that the plane wave carry can be discarded. So we have equation number 7 as the input field just outside the grating. We need to apply the Fraunhofer diffraction formula, which is this one as given in equation number 98, and u of x comma y is the output field, that is the field at the point xy at the output plane, and that is equal to e to the power iota kz over iota lambda z multiplied by e to the power iota k over 2z into x square plus y square, and of course the Fourier transform of the input field evaluated at the Fourier frequencies f is equal to x over lambda, fy is equal to y over lambda z. So you see that what we need to do, if we want to find the field u of x comma y, it means that we need to take then the Fourier transform of the field at the input plane, which is the Fourier of u of zeta and eta, and then we need to evaluate that Fourier transform at the Fourier frequencies fx is equal to x over lambda z and fy is equal to y over lambda z. Okay, now let's take the Fourier transform of the input field. So the Fourier transform of the input field is equal to Fourier transform of the cosinusoidal function, cosinusoidal grating convolved with the Fourier transform of the two rect functions. And this is the convolution theorem that we have applied. So you see that the cosine function carries the Fourier transform of 1 plus m times the cosine functions carries three delta functions. One is delta of fx comma fy. This is the Fourier transform of 1, and there are two other Fourier transform containing two delta functions with the values of m by 2 into delta of fx plus 1 over l comma fy, and the other one is m by 2 into delta of fx minus 1 over l into fy. So three delta functions arise due to the Fourier transform of the 1 plus m times cosine grating. And you know that then there is a convolution sign which we have written in the third row of equation number 99, and the two rect functions have been given in terms of the sinc function. The Fourier transform of these two rectangles are given in the sinc functions. So 4w square is equal to 2w from each sinc, and so there are two sinks, so we have 4w square, and the one sinc is a sinc of 2wfx, the other sinc is 2 sinc of 2wfy as in equation number 99. So we are introducing A is equal to 4w square as the area of the grating. So in introducing this A over here, then the Fourier transform can be written as A into sinc of 2wfy. So sinc of 2wfy is a common term which we have taken outside the curly brackets, and within the curly bracket then we have the convolution which we have done over here. So the convolution mean that the sinc function, that the argument of the sinc function will be replaced by the arguments of the delta function. So this sinc function, in the first sinc function fx will be replaced by so you see that the argument of each function, each sinc function will be replaced by the argument of the delta functions. So having done that one, we have obtained equation number 100, in which we have, you know, that three sinc functions with, of course, the values of the delta function argument has been replaced, the fx values in the sinc functions has been replaced by the values of the arguments of the delta function. Okay, now we have to evaluate this Fourier transform at the Fourier frequencies, which is fx is equal to x over lambda z and fy is equal to y over lambda z. So substituting these values as in equation number 101, we have shown the expressions. So you see that what we have done is that we have replaced fx by x over lambda z, and wherever fy will occur, we shall replace the fy by the value y over lambda z. So having done so, we have obtained equation number 101. So you can see that fx, fy and fx have been replaced by their corresponding values given in the parentheses. That is, fx is equal to x over lambda z, fy is equal to y over lambda z. So equation 101 is our final results of the Fourier transform of the input field having been evaluated at the Fourier frequencies as listed. Now the Fourier field, for the Fourier field we have to plug in the Fourier transform in the equation. That is, in this equation we have computed the Fourier transform in equation number 98. So we are going to plug in the values of the Fourier transform evaluated at the Fourier frequencies, and then the far field, the Fraunhofer field or the far field becomes equal to as given in equation number 102. So you can see that we have u of x comma y. The first two contains some exponent containing iota, and then we have sinc function, sinc of 2wy over lambda z, and within the curly bracket we have three sinc functions. So sum up of three sinc functions actually. So this is equation number 102, giving the full description of the field at the point xy at the output plane. Now we can plot this field, that we can plot the one-dimensional form of this field has been plotted, because the two-dimensional form is difficult to analyze. For 1D plot, what we do is that we take only the x components of that field, and we can reject the other field. We can reject the or discard the y component. So sinc containing y will be discarded, and only the sinc containing x will be retained. So you see that, and the exponential, in the exponent we have e to the power iota k over 2z into x square plus y square. So only x square term will be retained. But you know that we are going to plot the absolute value of equation 102 in one dimension, because these are the complex values containing two complex constants, and there is containing two complex exponents, and there is also iota lambda z in the denominator. We cannot use, you know, that complex variables, complex statements, complex mathematical calculations cannot be plotted. So we need to take the absolute value of each of these. So the plot of the absolute value of the three sinc functions within the curly bracket is shown. So here we are just plotting the terms within the curly bracket, because the other two terms are insignificant when we take the amplitude, and we have discarded the sinc of 2wy or lambda z because it is y dependent, so it would not matter. So only the three sinc functions within the curly bracket have been plotted over here. So look at these plots. The central one is the sinc of 2wx over lambda z, and the other two sincs are on the side. One contains m by 2 into sinc of 2w over lambda z. Within the square bracket we have x minus lambda z over capital L, and on the left hand side we have m over 2 multiplied by the sinc of 2w over lambda z, and within the square bracket we have m plus lambda z over L. So you see that these are the sinc functions, and we have used the value of m in order to plot this one. Now you can look at the width of the central thing. The half width is given by lambda z over 2w, and the other two peaks of the sinc functions are located. One is at x is equal to plus lambda z over L, and the other sinc is located, that is the center of the other sinc is located at x is equal to minus lambda z over L, and the central sinc is of course is located at x is equal to 0, as is also obvious from this one that this sinc is centered at x is equal to 0, and from this one we can see that the right sinc function is centered at x is equal to L lambda z over L, as obvious from the mathematics also. And you know that the left sinc function, the peak of that one also exists at x is equal to minus lambda z over L, as obvious from this mathematical terms that we have written on the above of each peak. And you know that the separation of the peaks has also been given, and the width of the half width of the central peak has also been given, which is lambda z over 2w. And these plots are given for m is equal to 1, and these are the one-dimensional plots, so that we can visualize. You can see that there are side lobes also. So in the central peak, the side lobes are larger in amplitude, and of course they decay on both sides, and then we have the other two sinc peaks, and of course there are also some side lobes which also attenuate as you go away from the central peak. So the plot of the absolute value of the three sinc functions within the curly bracket is shown in the figure. Separation between the consecutive peaks is lambda z over L. So you see that you can see that the first peak on the right hand side is located is at a distance of lambda z over L from the central peak, and the leftmost peak is away from the central peak by a distance lambda z over L. These have been also shown in the diagram. So you see that you can see this diagram has been very well explained, and we have plotted this. These are the plots of the equation 102 in one dimensions using m is equal to 1. So to avoid the overlap between the sinc functions, the peaks of the sinc functions must move apart, and this is possible if L is very small compared with W, that is L is less than W. You know that W is the spacing between the two grating lines, and W is the half the width of the square aperture, and you know that the total width of the square aperture is 2W. So we are assuming here as L is much less than 2W, or you can also say that L is much less than W. That is, the grating must have high spatial frequencies, and you know that this is also obvious from this L in the denominator of this figure. If L is large, if L is small, then you know that the separation of the peaks will be greater on both sides, because L occurs in the denominator. So if L is small, the terms will be greater, so it will be farther away from the central peaks. Okay, so if we are using a grating of high spatial frequencies, then these three peaks associated with the sinc functions will be well separated from each other. And you know that when these are well separated from each other, we would be able to write the intensity expression. Otherwise, the intensity expression cannot be written. If there is an overlap between the neighboring sinc functions, an analytical expression for the intensity cannot be written. because then you know that in the while in order to write the intensity expression, we have to multiply these three sinc function peaks with the complex conjugate of these peaks, and then you know that analytical expression would be difficult. But if these are well separated, then of course the intensity expression will be given only by the square of the sinc functions in each of these expressions. So all these three functions in the curly bracket will be squared if the separations, if they are not overlapping if they are not overlapping. For an analytical expression of the intensity, we are assuming that the sinc peaks are well separated such that there are no overlapping or negligible overlapping between the neighboring sinc functions. So with this assumption, we can write we can multiply u with its complex conjugate to write down the intensity expression, which is given on the right hand side as in equation number 103. So you see that we have three sinc functions. Now these three functions and with their coefficients have been squared. So we have taken the square of these quantities because in the center we don't have the complex variables. All these three functions are actually real functions, and on the left hand side of these one, when we take the complex conjugate, these terms which contains iota will be cancelled out, will vanish out from the expression. So you see that 103 gives you the intensity expression. For the intensity plot shown in the previous slide, it is obvious that most of the optical power goes in the main lobe, and a negligible power and a negligible small amount of power will appear as noise. So how much optical power is distributed into the three orders? This will be computed from the coefficient of delta function as in equation number 99. The three delta functions along with their coefficients are taken from equation number 99 and listed as delta of fx, fy, and second coefficient of delta function along with the delta function is m by 2 into delta of fx plus 1 over l, fy, and the third delta function along with its coefficient is m by 2 into delta of fx minus 1 over l, fy. So these three delta functions along with their coefficients are given. The leftmost delta function has 1 as the coefficient. So now we are going to carry out the energy distribution in each of these peaks of the delta functions or the sinc functions. For that one, we are going to carry out the sum of squared of the coefficients of the delta functions. So three delta functions, three coefficients, 1 square plus m by 2 square plus m by 2 square. So that becomes equal to m plus 1 plus m square by 2 as in equation number 104. This is the sum of squared of the coefficients of the delta functions. Okay, now the optical power into the zeroth order. For that one, we are going to calculate the coefficient of delta of fx, fy, because this corresponds to the zeroth order frequency, and the square of this coefficient divided by 1 plus m square over 2. That is 10. That is the term from equation 104 has been used to divide the denominator. That is 1 plus m square over 2. So the coefficient of the above delta of fx, fy is 1. The 1 square is 1. So 1 over 1 plus m square over 2 is as given in equation number 105. So this will determine the optical power going into the zeroth order. So using m is equal to 1, and from equation 105 we obtain 2 over 3 multiplied by 100. That will give you 66.6% of the incident light contributes in the zeroth order main lobe. So you see that in the zeroth order 66.6% power will go. So what about the first order? The optical power into the plus 1 order is equal to the coefficient of the delta function, which corresponds to the first order is delta of fx plus 1 over l, fy. Its coefficient, you know, that is given above over here. So its coefficient is m by 2. So the square of that coefficient is m square over 4, and we are dividing it again by the total contributions from equation number 104. So we have m square over 4 divided by 1 plus m square over 2 as in equation number 106. So you see that again using m is equal to 1, and from the equation 106 we have 1 over 4 multiplied by 2 over 3 multiplied by 100 will give you 16.6% of the incident light contributes to the plus 1th order in comparison with the main order. in a comparison with the main lobe. In the first lobe in comparison with the zeroth order lobe, the power that will go into the first lobe will be equal to 16.6%. So similarly, optical power going into the -1 order is equal to the coefficient of the delta of fx minus 1 over L comma fy. We are putting the coefficient of this one, which is again m by 2, and the square of that one is m square over 4, and divided by the total contribution from equation number 104, and we have obtained this relation as given in equation number 106. So you can see that the term in 106 and the term in 107 are the same. It means that the same optical power is going in equation number 106 and in equation number 107. By the way, we have computed that one. So using m is equal to 1, and we find that 1 over 4 multiplied by 2 over 3 multiplied by 100 is equal to 16.6% of the incident light contributes in the -1th order in comparison with the main order of the light. So the total in the side, in the two sink, in the main lobe, the total contribution of the input power will be equal to 66.6%, whereas in the side main lobes, the power that will going into these powers will be 16.6% each. And you know that we have used some assumptions for that one, for this analysis, that is no absorption of light by the grating element. We have assumed that light is not going, that no part of the light has been absorbed by the grating, that is the grating is 100% efficient. And the second assumption that we have used is that side lobes with each sink are either absent or negligible, because we have not calculated the power going into the side lobes. We have just calculated the power going into the main sink lobes, that is the main sink lobe in the center and the other two sink lobes going on either side of the main lobe. So for that one, we have to assume that side lobes with each sink functions are either absent or negligibly small. So this is the end of slide number 48.